Hello, Modern Physics class. Alex O'Brien here, going to be talking to you about quantum computing today. So to start, what is computation? Computation is a very general term that describes executing an algorithm, which is just a set of instructions in order to automate a function of some kind. And this can be like a purposely built function or just a naturally occurring function in nature. An example of this, a simple example could be, as simple as writing down instructions for someone to mow your lawn or take care of your dog or something. Those are really basic examples they teach in computer science when you're first learning what an algorithm is. But another example of computation in nature is human DNA. So, DNA can be thought of as an algorithm that's read by a ribosome, which is, kind of the computer. It automates the function. The ribosome reads what the DNA is saying, and it executes the series of biochemical operations. It can be kind of hard to think that complex beings like us can come from such simple steps. But computation drives a lot of the complexity in nature. And so classical computation, it's a specific case of computation which uses electricity to represent its data. And so, a lot of people have heard of binary. It's ones and zeros. It's basically just, is there an electric signal? 1. If there's not, it's a 0. Each individual 1 and 0 is called a bit, and they're grouped together in groups of 8 and are called bytes. And so these bytes and bits are accessed and moved around using electronic transistors, which are conductive devices that control the flow of electrons. And these modern transistors follow Moore's law, and they've been getting smaller and smaller. They're close to the size of 10 or 20 atoms, I believe. And these transistors make up logic gates, which are the building blocks of computers. Logic gates, they take input. Generally, it's thought of as 2, but it could be more as the logic gates work in parallel. And examples of logic gates are like OR, AND, NOR, NAND. And so logic gates, there's billions and billions of them in computers, and it's combinations of, an AND gate. It takes in 2 electric signals. If they're both 1s, then it gives out a 1. Whereas if one of them's a 0, it gives out a 0 because it's an AND. It needs 1 from both. Whereas an OR, as long as one of the inputs is a 1, it'll give out a 1. I don't really have time to go super deep into logic gates. I wish I did, but they're pretty interesting. It's interesting how the flow of data is represented by those. And it's the interactions of the billions of these logic gates that represent the flow of data in computers. I like to think of classical, electronic computers as taking advantage of the properties of electricity. And this is sort of where you make the jump from classical to quantum. Quantum computers, they take advantage of the properties of quantum mechanics instead of electricity. Well, electricity is still kind of is still subject to the rules of quantum mechanics, but classical computers don't take advantage of the quantum properties of electricity. So quantum computers use particles that are entangled and in a superposition to manipulate their data. It was Einstein who described entanglement as spooky action at a distance. He just meant like particles, their state depends on each other even when they're not physically in contact. And so, classical computers, I think of it as a cascade of electric signals, is how computers work. Like the electric signal travels from one logic gate to the next. Whereas quantum computers are very different. And they're very confusing to me, at least. And so, they take these particles, they entangle them, and they put them in a superposition, and then they observe the system, and the particles affect each other instantly, and then, depending on how they affect each other, you get a different output. And it the big difference is in the time it takes, I guess, to do this, because electricity traveling, it's non-zero time. It takes time for the electric signal to pass, and it takes energy as well. Whereas, entangled particles, it doesn't take time for that. As soon as you observe one particle, it affects the state of the other particle instantly. They're connected some invisibly. And another difference as well is, instead of binary, 1 and 0, it's not a binary system. These particles can be in a state that represents 1, 0, and then like any superposition between 1 and 0, and these are represented by spins. Spin up, spin down, spin left, spin right, and they can be like spinning at any angle, to represent, spin up would be 1, spin down would be 0, and it can be anywhere in between, sort of. And so, you have collections of these superimposed particles. They're called quantum bits, or qubits, instead of, the 1 and 0, those are bits. These have the superposition between 1 and 0. It's a qubit. And I find this idea really hard to understand or like imagine. I'm a very visual thinker, and so I even have a pretty good understanding of computer architecture, and it still puzzles me a bit. And I think most people would think that it breaks the laws of physics. How can something affect one another without touching or without taking any time? And that's the power of quantum computing. It's the entanglement. The state of the particle can be directly tied to another without their physical interaction. And instead of cascades of entanglement, it's all one instant step. And applications of quantum computing are, it's hard to know it now because we don't really have any really good, functional quantum computers. And it's not really feasible for quantum computers to replace classical computers, due to like the requirements it takes to have a working quantum computer. That we can't have like a fully functional quantum computer now because we aren't technologically advanced enough, I guess. Like quantum computers, they need absolute isolation and close to absolute freezing temperatures to work, because having this isolation and freezing temperatures, it stops decoherence of the qubits, or it stops the quantum system from being broken down. It's similar to like the double slit experiment, when there's no observation, there's just a sensor at the end, you get the diffraction pattern. But if you have a sensor at one of the slits, it breaks down the quantum interference pattern. And so, we still don't even know if there's ever going to be a fully functional quantum computer. But there are some interesting ideas I've read about that, they pique my interest. I would be very interested to see if they happen one day. One idea is like a quantum chip. And so in classical computers, there's something called a GPU. This is in the von Neumann architecture. He's sort of the one that came up with the modern design of computers. The GPU is the general processing unit. It basically it handles all of a computer's mathematical operations. Data is passed into the GPU, it does all the operations, passes the output back out. So the idea would be to replace the GPU with like a quantum chip, a quantum processing unit. And this could be beneficial due to the processing speed of a quantum computer. And also another application, it's not only for increased speed, but like an interesting field in quantum or in computer science is simulation. And so simulating environments that are quantum is very difficult on classical computers. It takes a ton of computational power. But applying a quantum computer and quantum properties could help in facilitating that, I guess. I'm not really talented enough to sort of imagine how that would work, but I think it's an interesting idea. Something I read about was quantum meteorology, where they would use quantum computers to have very super detailed simulations of weather and weather systems. And this could give much more accurate weather predictions, I guess, or it's not even much more accurate. It's like if it was a real quantum computer, it could give perfect predictions. And I think that's a really powerful idea. And I know it could be sort of far off to think about, but it's been on scientists and computer scientists and mathematicians' minds for a while. An example is with Peter Shor. So Peter Shor developed Shor's algorithm, named after himself. And it was the first algorithm to display quantum supremacy, which basically just means it's mathematically proven that this algorithm can do something faster than a classical computer. I think it's faster, or it can do something that a classical computer can't. The Shor's algorithm is used to calculate prime factors of an integer. And so on a classical computer, there's a time complexity associated with an algorithm. It's just like as the size of the input increases, the time to perform the computation increases with it. And so with the classical computer, to do this prime factor, it increases exponentially with the input. And that's a problem because if you want to do really high numbers, it can take the higher the number, the longer it takes. It can take a lifetime to do certain different numbers. But Shor proved that with his algorithm, it can be done logarithmically. And so it's a difference between a lifetime versus hours or days. And I think that's a really, really promising idea. And he wrote this back in 1994, so scientists have been thinking about quantum computing for decades, and I think they'll continue to work on it until they come to some conclusion about whether or not they'll be useful or it can actually be done. And that's pretty much all I have to say. It's a really interesting idea, quantum computing. I definitely struggled to understand it myself, but I hope I was able to shed some light on it for everyone in the class. Hope everyone has a good Christmas and good luck on exams.